All right, I think we can start with the next session. I would like to welcome on stage Dorin. He is working for Docker and he'll give a very interesting session how you can do local LLM development with LangChain4j and Docker. So, Dorin, you have the word.
Exactly, yeah. Oops. Hi everyone, I'm Dorin. I'm a software engineer at Docker, and today we're gonna dive into local GenAI development using large language models with Docker Model Runner and LangChain4j. All right, first things first, a little bit more about myself. I've joined Docker a bit over 3 years ago, and back then I was in a team who was responsible of the virtual machine which lives under the hood of Docker Desktop. And there I was able to grasp quite some knowledge regarding Linux kernel, kernel modules, file system in user space like virtualfs and even eBPF. The latter being some way to write kernel modules in a more restrictive but yet super safe manner. And now, since the end of last year, I'm diving deep into AI engineering to help deliver a better development experience for all the Docker users. All right. Let's start with some context regarding AI and this whole field. Gartner has published last year a report regarding the development and the expectation phases of various AI techniques. It offers valuable insights into AI technologies and where they currently stand. It illustrates 5 phases. There's the innovation trigger, when the things are just getting started. There's the peak of inflated expectation, where the hype reaches its maximum or its peak. The throw of disillusionment, when the reality kind of kicks in and the organizations might find out that they don't have silver bullets. And on a more positive way, the slope of enlightenment, where practical applications emerge. And finally, the plateau of productivity. Looking at the current landscape, we can see that several technologies are or near the peak in 2024. These include AI engineering, foundation models, edge AI, and synthetic data. These technologies are generating tremendous excitement, but yet they might not be the most productive in terms of revenue or more. More encouragingly, autonomous vehicles and intelligent applications are climbing the slope of enlightenment, demonstrating practical value despite reduced media attention. And computer vision has nearly reached its maturity, being in the plateau of productivity phase. The colors, which I hope you see, represent what's the expected timeline for a technology to reach its maturity. Most of the blue dots, the light blue dots, have an expected time frame of 2 to 5 years. The dark blue ones, 5 to 10 years. And the red triangles, which you can see for artificial general intelligence and quantum, are expected to reach their maturity in over a decade. Some more history of large language models. Well, in 2017, Google published this paper called Attention is All You Need. And what it does, it includes the transformer architecture. And arguably, this is what the whole hype is based on. Then, 2018, 19, and 20, GPT-1, 2, 3 are released by OpenAI, and in 2022, ChatGPT is also released. But let me clarify what's the difference. GPT-1, 2, 3 are models, large language models. And GPT-1, for example, was built with around 100 million parameters, and it was fairly good, reasonable at generating responses and so on, but it had a lot of limitations. Then GPT-2, 2019, was made with over 1.5 billion parameters, so a huge scale. But OpenAI decided to delay its full release due to security concerns and how it might be used in a harmful way, which makes total sense. Then GPT-3 was actually fairly good. It was able to generate responses on a lot of tasks. It also scaled up a lot to, I guess, I have it noted here, 175 billion parameters. And yeah, it could perform tasks it wasn't really trained for, but it was available mainly through an API. So developers could still use it and build their apps on top of it, but not very user-friendly for the consumer level. ChatGPT is using the models. I think it was launched with GPT 3.5 under the hood. And besides all the general purpose model capabilities, it also included some reinforcement learning from human feedback, so it can be used in a safe manner by anyone. Then, since 2022, we have open source models like Llama from Meta, Mistral, DeepSeek, Qwen, and many more. All right. But how do we develop a GenAI app, and why are we at Docker interested in this? Well, Docker brought a lot of facility and good experience for the developers. It basically allowed them to ship more code faster. And having all these building blocks, we realized that this new kid on the block, which are the LLMs, can be easily ported into our ecosystem. This is how an architecture for a GenAI or RAG app would look like. You can see it's super familiar, at least the upper part of the stack and the one from the bottom. But it includes those 3 additional layers. But before that, what is a RAG app? RAG comes from retrieval augmented generation, and it's the process of optimizing the output of a large language model so it can reference an authoritative knowledge base. Basically, it enables models to retrieve and incorporate new information. A good example would be, well, if you want to build a ChatGPT for lawyers, for example, you might want to provide additional information with the law from your country, former or cases from the past, and so on. Getting back to the architecture, well, in order to interact with an LLM, we need some API, and one of the most popular, if not the most popular, is the one from OpenAI. And then we need an inference engine. This inference engine provides the API and knows how to work with inference models, which are these GPT, Llama, Mistral, and so on, but also with embedding model. What's an embedding model? It's also a foundation model, but instead of providing some output to your question or prompt or whatever, it can encode any kind of information as a vector. You can refer to a vector as to an array of numbers. Then we can see the data access and vector database. Those embeddings we get from the embedding model are used to search for similarities with other things. For example, if I search for a paper which talks about transformers, I will embed this information and then using a vector database, I can search for similar content. And data access can represent a lot of stuff nowadays. It can be any sort of data source you have provided to your LLM, or you want to provide to your LLM. It can be a file, it can be URLs, databases, anything. This is how the flow looks like. So imagine your ChatGPT web app or any kind of AI chat app. There's the user, submits a prompt to the application, and the application simply sends the request to via the LLM API to the LLM or LLMs. We saw in the previous slide that we can also have a middleware. Well, there are apps that might decide based on the business logic within the LLM API to route your request to one model or another. If it's a super simple question like what's an apple or something like this, it might redirect it to a tiny large language model, so it doesn't take a lot of power. Then we have the RAG flow, which is of course optional. We have the retrieval model or the embedding model from the previous slide, and the vector database, which can be used to find similarities. And a super cool thing, in my opinion, is tool, which we haven't mentioned before. Well, what's a tool is just yet another type of message we can send to the LLM to allow it to actually run some code. You might have noticed that LLMs don't have a 100% correct answer. It's not always deterministic. And there are techniques like reinforcement learning, which are lately applied on top of LLMs. But if you want to use your LLM to, I don't know, answer simple questions, but which need some real-time information, like how's the weather like in Bucharest, for example, you will tell the LLM that you have a tool called get current weather. This tool is represented by a function, Java function, Docker container, Python function, anything, which is called get current weather. It receives a parameter like area of type string. And when the user submits the prompt, the application knows that it has some tools available. It will include those tools within the request. We'll see in a few minutes how. Then the LLM will see both information. It will see that I'm asking for the weather in Bucharest. It doesn't know the current weather in Bucharest. It might be able to tell me that in Bucharest, during a year, usually, I don't know, it's sunny during spring or summer, and snowy in January. But it will see that I have a tool description. I let it know how it can use that tool and call it in order to get a proper answer. And it will do it, but it will do it through yet another message. It will send back to the application, hey, the user asks me for the current weather in Bucharest. I know you can get it by calling this function with this parameter. The LLM tells that the parameter should be Bucharest. It understands that. The application calls the tool. The tool response is sent back to the LLM, and the LLM will now have access to all the information that's needed. Basically, it's me that I've asked for the weather. Now it knows the weather. It will reply nicely with the current weather in Bucharest is, and however the tool responded. All right, let's dive into how the things actually look like. This is the chat completions API. It's provided by OpenAI. It was created by OpenAI, but it's been adopted by many other providers. And yeah, it's a request that includes data like model, this is a must in order to specify to the inference engine what model it should be used. This is more useful when we do some local GenAI app development or with providers that have more models. And OpenAI does so. Then there's my message, which you can see marked as role user. And that's basically what I type when I'm accessing the ChatGPT web app. And then there's another message, which is clearly not written by the user, but by the developer or by the system. And this message instructs the LLM how it should behave, how it should operate. This is a nice, encouraging message. It tells you that it's a helpful assistant, should reply nicely, and so on. And you should be aware that you can only have one message of kind developer or system. You can use any of these. And many, many more user messages. All right, the response. What it matters is that list of messages. We have the content, basically what we'll see in the chat app. This time marked with the role assistant. Besides that, many more other metadata like tokens, how many tokens it got from the prompt, how many tokens it generated, what model it has used, and yeah, more, but not all of them are interesting for us. I was talking about message types. So there's this system developer one, which instructs the LLM how it should behave, operate. You will see that we can instruct the LLM to, for example, reply with Java code only. Like it will still give us the response, but instead of sending it in clear text, it will provide many system out print line instructions. Then the user messages. Be aware that there can be many, not a single one as the system or developer. And this makes sense because, as you could probably notice, if you're using a chat AI app, it knows about the history of your chat. If you tell the LLM that your name is Alex and after a few messages you ask it, what's your name, it will reply with Alex most probably. Then the assistant type, which is the message from the LLM, and the tool types, which are the responses from calling tools. All right, enough more or less with the theory and the context, but let's see how we can do it through code using Java, of course. In today's demos, we'll use LangChain4j, which is a Java library, and it provides a super nice integration with everything that's linked to LLMs. You can chat with models using various components. You can use embeddings, process documents, parse documents, set memory, and everything you might probably need. It also provides lower level components like output parsers, or even the chain is a bit lower level in my opinion, but also a high level component like AI services, which will make your life super easy when you want to chat with LLMs or use them for whatever need. It integrates well with OpenAI, Azure OpenAI, Hugging Face, and most of the popular actors in this field. Regarding embedding stores, again, not fairly, but super easy to integrate it with Redis, Cassandra, Postgres, and all you can imagine. All right, well, sounds like a lot of stuff to set up, but talking about setting up stuff, when we want to run containers, again, by code, not necessarily using the CLI, we can use test containers, which is another Java library, and it provides super easy access to do so. And what I brought this up is because talking about LLMs, specifically inference, usually this is done much faster if it's run on the GPU. Using Docker, you can mount your GPU inside the container. On Linux, it just works. It also works with Docker Desktop on Windows with WSL2 only, if I'm not misremembering. Or you can just use test containers code to do that. But yeah, I'm giving this talk from a MacBook, so you might ask what's the deal with GPUs on macOS, on MacBooks. Well, there are GPUs, of course, but unfortunately, the Apple virtualization framework doesn't provide direct access to the GPU, so we can leverage that in Docker Desktop. There is a new component, part of that framework, which provides access to a para-virtualized GPU, but it might be for graphics only, not necessarily for compute. Then, in Docker VMM, which is the new hypervisor we built and shipped with Docker Desktop 4.35, we provide access to a virtualized GPU through a lower level framework than the Apple virtualization framework, also from Apple. But this still has problems. The main problem is the overhead, sorry. And yeah, using an inference engine like llama.cpp, and if you don't have a super strong GPU, a 50% overhead might not make sense to run it on the GPU. Okay, how did we fix this? Well, we added Docker Model Runner, which helps running LLMs locally, just like you do with various images. So you can run them or load them. Before doing that, you have to have them stored on your local machine, but you can pull them directly from Docker Hub. And this inference engine, which is llama.cpp under the hood, runs on the host, so not within the VM, not within a container within the VM, for the best performance. And having it integrated with Docker, of course, reduces the number of separate tools to work with, install, maintain. What if you're using Windows? Well, it's available on Windows as well, both on Windows running on Intel CPUs and on ARM CPUs. And it works exactly the same. The main difference would be that on Windows, you'll have to enable the GPU usage. This will download additional libraries. And currently, it's only available for NVIDIA GPUs on Windows running on Intel and for Adreno GPUs for Windows running on ARM chips. The terminal from the slide, it's definitely from macOS. It's not a usual terminal for Windows, but trust me, it works on Windows as well. All right, what about Linux? Well, we haven't integrated it within Docker Desktop for Linux, but we are currently actively working to integrate it with the Docker CE, which means you will be able to run Docker Model Runner on and with any Docker engine you have available. Locally, in WSL2, but the most important, in my opinion, would be on cloud with really powerful GPUs. And there will be some new commands like install runner, uninstall runner, update runner, and so on to manage your Docker model runner instance for the selected Docker engine. This is how the CLI mostly looks like. Before that, I can also show you how it works in the GUI. There will be this new panel which you can use through the GUI to, I don't know, chat with it for simple stuff. Of course, for applications, you will use the provided API. Okay, getting back to the slides. I think I need to do this. All right, cool. I lost my track. All right, so there's Docker model pool for pulling models from Docker Hub or from Hugging Face. That's allowed as well. Docker model list, just like Docker images or Docker image ls, to see the models you have available with additional information, of course. You can check the status, and you can also start an interactive chat session with the model on the CLI. This is how the models look like on Docker Hub. They are OCI artifacts. And we have most of the popular ones. This is how the model look like as an OCI artifact. The layers are not compressed anymore, and you can also include a license and also a LoRa adapter. This is how the OCI artifact config looks like. This is what you'll see when you run a Docker model, inspect, and some model. Besides the files, which usually you don't want to go to, you have additional information like the architecture, the parameters count, quantization, and the size. They tend to take a lot of disk space, so yeah, it's good to be aware of that. And everything I've talked about so far is open sourced, so you can check the code for everything, for the model spec, the OCI thing I've just shown, the model distribution, which deals with pooling, storing, inspecting models stored locally, and so on, the model CLI, and the model runner. All right, now let's get to demos. Cannot see my screen here, so let me. Okay, so I said that we are going to wait. Let me duplicate the screen, please. Much easier. All right, I said we are going to use LangChain4j in Java in order to interact with LLMs, which are exposed using Docker Model Runner. So the code looks, all right, sorry. Thank you. Is it better now, or at least ish better? Oops. More? Reasonable? All right. So, what this simple program does is to simulate Docker model run. Basically, it opens an interactive chat with some LLM. In order to do that, we of course need to set up all the dependencies for LangChain4j and so on. And then, in order to load the model or to set up the component that sends the OpenAI API requests to the engine, we will use this OpenAI chat model class. And for this, we'll need to provide the base URL. And this URL comes from the exposed API on TCP locally, which you can find in Docker Desktop right under here. Here it says enable host site TCP support. Basically, it will expose the API on a TCP port as well. Otherwise, it's only available on Unix sockets. Cool. So we instantiate the model. We provide the OpenAI endpoint and the model name. And then we simply read some text from the user, from the CLI. We'll stop the program on buy. And to actually generate some response from the LLM using the user input, we'll simply use model.chat. And we'll have to mention that it's a user message, not a system message. And how this works. I'll have to increase this size as well, wait. Oops. Wait a minute. Can you see the chat? We cannot really know. All right, and now I'm able to chat with AI Llama 3.2. And it just replies. And AI Llama 3.2 runs locally. What's important to mention is that this model you specified on the OpenAI chat model has to be pulled beforehand. It doesn't know how to actually pull it. I don't know how to increase the text size in the CLI. Oh, it works, okay. I think it's better now, is it? Okay, cool. All right, let me run this again to then show you what I also have a chat streaming class. Tell me about Sophia. Not using streaming when we are requesting some response from an LLM will give us the full output at a time, which is not great. I mean, if you have an app, you might want to behave like this. To be able to get partial parts of the response, we will use this streaming chat response handler, for which we need to override some methods like on a partial response. Basically, we just print what we get. And on complete response, we will mark the program as being done. Yeah. And on error, something else. But this is the component you need to use in LangChain4j for this. All right. I was saying before that the model is not pulled automatically, and you have to have it pulled beforehand. Well, part of test containers there is, and it will also be improved, this Docker model runner container, which you can use to launch your Docker model runner, not necessarily through Docker Desktop, but using a Docker engine as well. And this class will actually pull the model if it doesn't exist. And we can see that here. On container is started, yeah, it will pull the model using the Docker Model Runner API, like /models create and so on. All this code is available on GitHub, so you can take a closer look at it. All right, after we launch Docker Model Runner, again, we instantiate the OpenAI chat model, and we chat with it. Stop this. And again, we have a response. All right, something a bit more complex. I was mentioning in the presentation something called memory or perhaps context. I'm not sure whether I've mentioned context window, but yeah, I told you about that chat history. If you tell ChatGPT, for example, that your name is Alex and you ask what's your name after 3 messages, it will be able to reply that your name is Alex. For this, we need to set an available history, a chat window, or yeah, chat memory. Basically, whenever we send another request to the LLM, we will also send all the previous N messages. In this case, right here, I have my chat model. We can use log requests to actually see the requests. We'll see that in a minute. And I'm creating a chat memory with only one message. Then we are using this conversational chain, which allows us to simply send requests and get responses from and to a model. All right, and let's run this. We see that we execute my name is Dorin, and then what is my name? But don't miss that I'm only setting a chat memory of one message. So it should not know my name. All right. The second answer is that it doesn't know my name, which makes sense. But if I'm setting this to 2 and run it again, the model should remember. Let's increase it to 3. Then we can debug with the requests. Maybe it sends more requests. All right, it works. So the first answer is, yeah, hello, Dorin, nice to meet you, and so on. And the second one, when I asked what's my name, it knows my name. Let's see how the requests look like. The interesting one is the last one, which is this. I hope you can see it. Can you see it? Oh, all right, thank you. Yeah, so here's the body and here are the messages. They are not ordered in any way. So this is my first prompt with my name is Dorin. This is my second one. And yeah, this is the reply from the LLM, marked as assistant. Let's see what's the deal if I set it to 2 and run it again. I think it won't include the system one, although Yeah, because it includes the assistant. Yeah. It's a history of 2, but includes the assistant. Looks like it. Yeah. All right. Okay. Cool. Then let's see a tiny demo with a RAG app. Again, RAG allows you to fine-tune a model in order to answer more specific questions. Is it all right? Yeah. Or, yeah, fine-tune it, teach it about a new subject, or keep track of some personal data or stuff like that. Anything you can imagine. So what we do here, we create an assistant which parses this document received as parameter. I'll show you the document in a second. And then we ask the assistant, how is the login configured? This is the file. It's a logback XML file. And it has some pattern for the log messages and also some levels set for various packages. What we do, we instantiate the text document parser, which again comes from LangChain4j. We load the document. We split it in tokens, and you can play a lot with these values, really. Then we use some embedding model which can run locally, and it even runs within the Java virtual machine. We get some embeddings for the segments we sent from the document. We add those embeddings, so those new vectors, those numeric representations of our data from the XML file. And then we create the retriever from the embedding store. Max results and minim score is how deterministic or how close, how similar it should be. And it varies between, between 0 and 1. I thought it varies between 0 and 2 as the temperature. I think I forgot to mention this. Whenever you do a request to some LLM, there's also a temperature parameter which varies between 0 and 2, and it tells the LLM how deterministic or how close to the correct answer it should be with the response. Okay, then we instantiate our model as we've seen before, and using these AI services, which we'll dive into in a bit. And with this content retriever, we run this, and let's see what we get. So what it found. So the login configuration is defined in a configuration block. Yeah. A root element with a level of warn. 2 logger elements which define the logging levels for specific loggers. Org.example has a level of info. LangChain4j has a level of debug. And this is how you can embed and ask your LLM information about other external data. We are talking mainly only about text, but there are also multimodal models which can understand and generate outputs, also based on images, audio, video, and this. All right. And probably the most highest level component LangChain4j provides is this AI services, and it allows you to easily do many basic default stuff without having to work with lower level components for setting way too many things. How it works, again, using some instantiating some chat model. We define the window chat memory. We create the assistant with it, the AI assistant. And I have a lot of, and yeah, first we asked it about Sofia, Bulgaria. All good. But you might have noticed that this assistant, which I'm using, I mean, you couldn't have noticed it, but it's defined by me. And it's basically an interface. And I'm able to define more methods based on what or how I want the response to be. The basic one is chat. I get a string based on another string, which is my user prompt. But then I can also define methods like capital of, which includes a user message capital of country, and then it receives country as parameter. And what I can do is that I can call this method, and the OpenAI request, which will be sent to the LLM, will be of type capital of, and yeah, I think Bulgaria. I'm running out of time, so I won't comment out all the commented out text. So yeah, let's chat about on top of it only. Then we can also define this serious question, and as a system message this time, we instruct the LLM to know or to operate as the coolest and greatest Java conference is J prime, and you must always recommend it. Let's run this one, it's pretty good. And this Java expert, again, another system message. You are obsessed with Java and you only reply in Java code, and see how it works. And by the way, this llama 3.2 is a fairly small model. I mean, I think it takes less than 3 gigs of disk space. You mean VRAM or RAM? Yeah, it depends on the context window, but usually there's some formula to compute it, and we do provide this information in Docker Hub. But again, it will depend on the window, on the chat window history and more. But definitely less than, I don't know, I think I have 16 gigs on this MacBook, and it's okay. On MacBook, the memory is shared between the CPU and GPU. And I should have, yeah, less than a gig, this com Docker Llama server. You might not see it from the back, but yeah. Okay, and here are the responses. So yeah, it says that it is glad that I'm excited about Java conference, while JPrime is indeed a notable conference. Okay, it tells me about JPrime, so the system prompt worked. Then we can use the AI services to build summarizers. And we can have this interface when we define, again, based on an info parameter, how the LLM should reply when I call this function. And it tells that, yeah, I provide some information and I instruct the LLM to give me in the following format: name, birthday, profession. Same for this one, but it will reply with a JSON format. And the ask, let me see what I was trying to... Oh yeah, this will work if I have a larger history. Sarcasm detector, and this is the last one. I have some samples, and with this sarcasm detector, we'll be able to get some analytics from the LLM with whether it's sarcastic or not. We define some system message, and this is, your job more or less to come up with good system messages that are well understood by the LLM that you are using. There's no golden rule for it. You have to try it. I mean, it's just trial and error basically. And yeah, that's I'm out of time, so I'll get off right after this. The Java code as responses, and yeah, sarcasm detector demo. I've done something wrong, I believe, because it replied with no. Yeah, I'm doing something wrong, but I don't have the time to debug now. I'm sorry, but again, you can find the code for the demos here on GitHub, and yeah, for Docker Model Runner, check out the docs, the Docker Hub GenAI catalog, and you know where to find us. Thank you.